Well, hello, welcome. I want to encourage you, if you haven't already done so, to make sure you watch the video on the new way of doing gravitational potential energy, because this particular video here will refer back to that. It's actually a really clever way to use this new idea of gravitational potential energy. And the question is to calculate the escape speed, or sometimes called the escape velocity, for a planet. And typically, like in our textbook, they calculate the escape velocity for Earth. And first, let's talk about what escape velocity means. Imagine you could throw a ball up into the air. And of course, after a while, it's going to come back down into your hand. But if you throw it faster, it's going to take more time to return to your hand. So the idea of escape speed is, with what speed could I throw this ball and never expect it to return to my hand? And we have to imagine things like there's no atmosphere to slow it down or anything like that. So we have this very kind of pure, spherical, perfect little planet, no atmosphere and nothing in the way. There's no other things in the universe that'll ever get in the way, which of course is completely ridiculous. But if that could happen, with what speed could I throw it and have it never return? And you might think, well, there is no such speed because gravity will always attract the ball back to the planet. But what if we make it to infinitely far away? Infinitely far away is that one spot we can imagine where we will never have a force of gravity acting on the ball towards the planet, and for that matter, the planet towards the ball. So this is a very imaginary idea, but we could approach the escape speed and still expect it never to return. Now, again, we don't do this. Typically, we have propulsion on things that we launch from our planet. So, we have rockets and things like that. But this is imagining no propulsion of any kind. So how would we approach a problem like this? Well, we use the idea of energy, conservation of energy. So let me draw a little planet here. I'm not going to be able to draw this to scale because I'm going to draw something that represents infinitely far away, which in the limits of my paper, this is about as far out as I can go. So here's the little ball. And I'm going to give it some initial speed. Now, in my description, I said I'm going to throw it up. But remember, when you're looking at a picture of a planet, up just means away from the surface. Okay, so this can be up here. And I'm expecting this ball to move way out here. It's going to be getting slower all the time, of course, because the force of gravity provided by this planet is accelerating the ball towards the planet, making the speed get slower. But what we want to happen is it will slow down to the point of reaching zero speed, so v equals 0, when it gets infinitely far away. So we'll say at infinity. Well, what else do we know about the ball when it's infinitely separated from the planet? In our new way of doing gravitational potential energy, that is also the location where the potential energy is defined as 0. Okay? So there's 0 potential energy when two objects are infinitely separated from each other. So I could say, because the speed is 0, the kinetic energy reaches 0, and the gravitational potential energy is also 0. So I have this system with 0 energy. Well, conservation of energy means if I expect it to end with 0 energy, I just have to make sure it begins with 0 energy. Now, this will really confound you a little bit. If you're saying, I have to begin with a system where the ball is moving and yet there's 0 energy. How can that possibly be? Well, remember, if the ball is going to be thrown, we've got kinetic energy, and it's also going to be having some gravitational potential energy, which is always negative. It's got to be less than 0, because 0 is what it has when it's infinitely far away. And anytime things are closer than infinitely far away, they have to have lower gravitational potential energy. The only way to get lower than 0 is to have negative numbers. So the initial kinetic energy and the initial potential energy have to add up to be 0, because the final of those two energies also add up to be 0. Okay, so how do we write expressions for these? Well, my kinetic energy, we always write the same expression. 1/2 times the mass of the ball times the initial velocity of the ball squared. Okay, so we'll say this little velocity vector is the initial velocity of the ball. And how do we write the gravitational potential expression? Okay, I'm going to add it to it. This, if you're in my class, I'm going to call it equation 31 on the green page. It's negative g, our gravitation constant, times the product of the two masses that are interacting, that's the planet and the ball, divided by the separation between their centers. The center of the planet and the center of the ball are separated by the radius of the planet. Okay, remember, we don't say there's zero separation when it's on the surface. That's actually the separation equal to the radius of the planet. Okay, so here's my kinetic, here's my potential. They have to add up to be 0. All right, so how do I make these add up to be 0? Well, they must be equal and opposite to each other. So I could say that my 1/2 m times the initial velocity squared must equal g times the product of the masses divided by the radius of the planet. Okay, all I did was I moved this term over to the other side. Now I can start canceling some things out, because what I'm looking for here is the initial velocity of the ball. So I'm going to move everything over. The mass of the ball, notice, shows up on both sides, so that can be canceled. I'm going to take this 1/2 and just get rid of it by multiplying both sides by 2. So times 2 will cancel out, and that'll bring a 2 up here. And then I need to square root because this is squared in this expression. So if I solve for the initial velocity of the ball, I get the square root of 2 times our universal gravitation constant times the mass of the planet over the radius of the planet. Now, a lot of physics students are tempted to just want to memorize equations. So you'll call this the escape speed velocity. But I want to warn you against the danger of that. When you're dealing with questions like this and related questions, like we talk about orbits and we do all kinds of other things with gravitation, the formulas start to look really similar to each other. So don't try to do that. This looks a lot like the orbit equation, for example, for a circular orbit, except it doesn't have a 2. So don't do that. Learn the physics that gets you to these relationships. And the physics is something that should be pretty familiar. Conservation of energy, showing that the total at the beginning and the total at the end must be the same. Now, it's a clever application of that. The fact that they have to be 0 both places, that's a little bizarre. We've not done it that way before. But this is the beauty of the new way of doing gravitational potential energy. We could not solve this with the traditional MGH version of potential energy, because as we throw the ball up away from the planet, that gravity is getting less and less and less. So we can't use little g like 9.8 as though it were on the surface of the Earth. Okay, so then we could take any planet we want to, put in its mass and its radius, and we'll have the escape speed for that particular planet. So hopefully this helps maybe amplify a little bit what you've already read or seen. It can help you maybe if you're asked to solve a problem like that or something similar. Thanks for watching.